Now, our second talk of today, this is Florian Ricour, who's going to talk to us about carbon sequestration by the biological carbon pump. Over to you, Florian.
Yes, thank you. All right. Sorry, I had an issue with my screen sharing. Do you see it now?
Yes, I can see that
Yes.
fine.
Okay, perfect. Okay, so first of all, yes, thank you for the invitation, Adrian. I also finished my PhD last year in May, and I'm going to present you the work that has been published in Nature Geoscience, entitled Sensory Scale Carbon Sequestration Flux Throughout the Ocean and by the biological carbon pump, so by myself, Lionel Goudy and Louis Legendre in Villefranche, where I did my PhD, and Marion Jelen and Timothy De Vries. So this presentation is about the fact that carbon sequestration by the biological carbon pump is not exclusive to the deep ocean. So I know that Manon explained a bit already this scheme, but I'm going to go through it. So basically, the biological carbon pump is characterized by three export pathways. So you have the production of organic carbon in the euphotic zone, and this organic carbon is exported either through the gravitational settling of particles, so particulate organic carbon, by the gravitational pump from the export depth until the bottom of the ocean. Then you have the biologically mediated pump, which is basically two sub-pumps. So you have the vertical migration of organisms on a daily scale and also on a seasonal scale. So basically, you have organisms that will feed at the surface, and then they will transport this ingested carbon at depth, which will be remineralized. And then you have the less well-known physically mediated pump, which is related to the physical circulation. So it is the transport of dissolved organic carbon through the mixed layer pump, which is the succession of like shallow and deeper mixed layers. And then you also have the transport of carbon by the eddy subduction pump and the large-scale subduction pump. So once this carbon is exported at depth, it is a part of it will reach the sediments by the gravitational pump, which is a very small part, but you will have most of it that will be remineralized. And once this biogenic DIC is remineralized, the question is, how long is it going to be sequestered from the atmosphere? And so when I say in the title that this is an old paradigm, I mean this part on the right is that we see it as a discontinuous way, in the sense that, okay, if you have some biogenic DIC that is remineralized in the first 500 meters, you would not think that it may be sequestered for more than 100 years. So basically, the commonly used assumption is that sensory scale sequestration of biogenic DIC only occurs below 1,000 meters. And I'm going to show you why we want to revise this assumption. So basically, our work uses the F100 factor of Siegel et al. 2021, and it is defined as the fraction of water at a given location and depth that will remain in the ocean for at least a century. And in other words, it can be seen as the representation of the fraction of biogenic DIC flux that can be sequestered for more than 100 years. And here I'm showing you a map of this F factor at 500 meters. And you directly see that you have regions here, the northern part of the Indian Ocean, the Eastern Pacific, and the Antarctic margin, where you are already above 0.5. So it means that if you think about the common assumption that sequestration only occurs below 1,000 meters, you would miss sequestration in those regions, while on the other end, if you go to 1000 meters, you have regions where you do not have a factor of 1, which would mean that you have full sequestration for at least a century. So in those regions, again, if you say that, okay, sequestration occurs fully below 1000 meters, you would overestimate the sequestration flux in those regions, meaning the northeastern Atlantic and the Antarctic polar current. And you can also play at different depths. So if I'm going to 2000 meters, and then I'm going to 1, you see that even at 2000 meters, you do not have F factor equals to 1 everywhere. So it means that not all the IC is sequestered at 2000 meters. If I'm going just to show you a bit at 320, again, you see that you have regions where you already have high values for the F factor. So yes. Especially also in the northern parts of the Indian Ocean, also in the Eastern Pacific. So on average, you see that even at shallow depth, you still have, on average, a factor of 0.2, which really put the question of, okay, we need a new concept about this sequestration. That's where the concept of converse comes in. So it is defined as the continuous vertical sequestration concept, and it is based on the distribution of this F100 factor. So if you go back to this part, instead of a discontinuous way of sequestration, we look at a continuous way. And if you look at the median, the global median F100 values, it shows that between the surface up to 1000 meters, it increased quite rapidly. So you are between 0.62 and 0.7. And then progressively go up to 1 at the seafloor, meaning that 100% of the pelagic DIC is retained for at least a century. So the point of this work is that now we want to see the sequestration flux by the BCP as this new view. So you still have the same scheme than before, where you have the biological carbon pumps, so the free export pathways. Part of this organic carbon exported reaches the sediments and is sequestered for a long period of times, and the other remineralized DIC will partly be sequestered depending on the local conditions and the depth reached by this remineralized DIC, and part of it will be released back to the atmosphere. So how do we compute this sequestration flux? So I'm showing you here different kinds of profiles. So basically, we have the F factor that comes from the model for each pixel on the map and for each depth. But we need to compute the remineralization flux. And here I'm showing you different kinds of remineralization fluxes in 4 different regions. So you see that you have different strengths, so to say, of remineralization flux here on the left. Then you have different profiles of the F100 factor, where you can see that at 1000 meters, the F100 factor is already around 0.8 near the Arabian Sea, where I showed you earlier that you already are at 0.5 or more at 100 meters. But on the other end, you see that near the eastern coast of the US, you are only at below 0.2 at 1000 meters, and then it reaches quite rapidly a higher value at 2000 meters. And when you multiply this remineralization flux with this F factor, you get the sequestration flux. And you see that maybe it was not so well known, but you can clearly see that the maximum of the sequestration occurs above 2000 meters and sometimes above 100 meters, as for the Arabian Sea. And so you see that if you compute the percentage of total sequestration, you already reach 50% of the total sequestration at a given pixel for the water column before reaching the depth of 1000 meters. So it would imply that if you think about sequestration as only occurring below 1,000 meters, you would miss quite a bit of the sequestration flux. So in Converse, we have 7 versions. I'm not going to go into big details here, but basically what we need is to have, we don't need 7 versions, but we do need to find different ways to compute the renormalization flux. So for this, we used both particulate and disorganic carbon data derived from the paper of De Vries and Weber 2017, as well as the well-known Martin's law for the attenuation of the downward carbon flux. And so for this, we are going to use different export values, one from De Vries and Weber and one from Hansen 2012. So basically, you have 3 petagram of carbon of export for Hansen 2012, and I think it's between 7 and 8 petagram of carbon exported for De Vries and Weber. And we use different export depths, either 100 meters or the base of the euphotic zone, as well as different kinds of renormalization factors. So for the first 3 versions, those are all the same, except that we use a constant value for the B factor, or geographically variable value, or even a zonal one, a regional one. And we compute the BGP using Martin's law, the migrant pump, but only the daily migrant pump, because we do not have enough data for the seasonal migrant pump. So this is derived from the value of the export of particulate carbon. And we use an export ratio for the mixing pump, because for the mixing pump, we need disorganic carbon data, and we do not have it for like an empirical law. So we use it from model data from De Vries and Weber. The C4 and C5 versions are from the model. They are used the data from De Vries and Weber, and here you have the single version, which uses the base of the euphotic zone for the export. And finally, and I'm not going into the details, but you have the C6 version, which only uses export ratio for the BGP and mixing pump. And finally, the C7 version, which is the same as the C1, but we use a different expression of the mixing pump. So we use a derivation from the particulate organic carbon export. That's maybe the most boring part of this talk, but this is over. So I'm just going to show you some maps, because if you read the paper, you'll see that we have a lot of tables, a lot of numbers, and a lot of maps, and sometimes it's not so user-friendly, reader-friendly. So here this is also available online, but basically you can compare the different results for the different methods. And so here you have the representation of different export values from Hansen 2012 and De Vries 27 for the export at the base of the euphotic zone. But what's interesting is that if you compare the BCP value for the C1 version and what you would get if you consider the sequestration only at 1,000 meters, you see directly that you have an underestimation of the carbon flux sequestration. So if I'm moving a bit here to the North Pole, you see that if you consider that sequestration only occurs below 1,000 meters, you clearly miss some patterns here. And it is even more striking if you look at the Arabian Sea, because if you've seen it before, you see that the F alert factor for the Arabian Sea is quite high, above 1,000 meters. So if you do not consider it, you would miss a lot of sequestration. And again, you can do that for every different versions. So if I'm taking the C4 version, which is the version which has the highest BCP sequestration flux, if you compare it with what you would get at 1,000 meters, you already see that clearly in some regions, due to the fact that you do not consider a continuous sequestration pattern, you would miss a lot of the sequestration. So we've seen the vertical profiles, we've seen the global maps, and now I'm going just to show you some numbers. So basically, with Converse, we have revised the estimations of carbon sequestration by the BCP, and we also have looked at different components of the BCP. So if you look at the numbers for the gravitational pump, we have computed sequestration flux, on a global scale, between 0.6 and 1.9 petagram of carbon per year. For the mixing pump, so the circulation pump, we have computed global sequestration flux from 0.13 to 0.45, which is not negligible. And if you look at the dial migrant pump, you see that you also have non-negligible values comprised between 0.11 and 0.26. So the first point here is that you see directly that the migrant and the mixing pump are clearly important in the total sequestration, and that you would not get them if you do not take the continuous framework. And if you look at the full BCP, you are between 0.9 and 2.6 petagram of carbon per year. And the funny thing is here that if you compare with the ratio of the BCP over the POC flux at 1,000 meters here, we have estimated that the sequestration flux should be between 2 and 3 times higher than what you would get at the fixed reference depth of 1,000 meters. And if you compare at 2,000 meters, we are between 3 and 6 for the C4 version. So if you want to remember really some key points for this talk, using this new framework called Converse, we have found that, and I just showed you that the global sequestration flux would be up to 3 or 6 times higher than what you would get if you use a fixed reference depth at respectively 1,000 meters and 2,000 meters. That the mixing and the migrant pumps contribute between 20 and 34% of this global sequestration flux, which is not negligible at all. And that if you use this fixed sequestration depth at 1,000 meters, you would miss between 47 to 68% of the global sequestration flux, which would be even worse if you use the fixed sequestration depth of 2,000 meters, because it would be up to 88%. So if you want more information, those visualizations with all the maps are available at this link. And if you want to contact me later on for questions, you have my contacts here. So yeah, thank you for your attention.
Excellent. Thank you very much, Florian. So, questions for Florian? So either put them into the chat or just raise a hand. So I'll ask a quick question just while we're waiting if people have got questions. So you're using a specific estimate of the ocean circulation here.
Yes.
How sensitive is it to that choice?
What do you mean? You mean that's the F factor? I mean, the caveats with this approach is that the F factor is so it's from a ocean sequestration model. But the thing is that it is for actual model of the ocean, and we know that this factor could change with climate change.
Mm-hmm.
So that's the caveat for this approach.
Yeah, I guess
as well as the remediation factor, which can also change.
Yeah, yeah. Dave, you got a question? Dave, I think you're on mute. No, still can't hear you, I'm afraid.
Can you hear me now?
Yes, can hear you.
Zoom decided I didn't have headphones. Yeah, it's not really a question. I was sort of seduced into the attending this because I saw the thing about deep water, and of course my interest is in really shallow water. You know, we're working in the Irish Sea, which is average depth of about 70 meters.
Uh-huh.
Is this sort of approach you've taken applicable in a situation that shallow, or is that governed by a whole lot of different processes, do you think?
So you said that you are working in environments where the water depth is up to 70 meters, right?
70, yeah.
70. Well, for me it could work. The F factor is, well, I can show you here maybe.
So basically, that depth is
Yeah,
no
it would be
sequestration at
close.
all.
It would be close to zero, but
That's what we thought, but I was
yeah.
just intrigued. Yeah.
Thank you, Dave. Any other questions people have got? Say, either type them in the chat or just put their hand up. So, Florian, I've got another question since I can use my power as host. You mentioned climate change. So, do you have an aspiration to apply this to something in a forecast model?
Well, I would say that this approach is not implemented in current biogeochemical model, and for modelers that look at the sequestration fluxes. But in terms of forecasting, I mean, it could be used, obviously, but the thing is, it depends on the time scale of the forecast, because the current values of the F100 are for the current ocean, and I don't know what would be the values if you look for in the next 50 or next 100 years. So yeah, I'm not sure.
Yeah, I mean, I guess one of the reasons I ask is because, the current interest of marine-based carbon dioxide removal.
Yes, that was something we talked during the review. Could be used for this. I mean, this is based on the paper of Siegel, which just basically simulate the injection of CO2 at different depths and look at the sequestration time frame. So technically, I see applications of this framework for those kind of approaches, but we didn't go far with it. But this is the point that has been talked and discussed. So I guess some work should be done on that.
Yeah, interesting. Thank you. Any questions? People must have questions, surely. I think people are slow out of the blocks in January. They're still, minds are in hibernation, maybe in the Northern Hemisphere. Any other questions or comments? I say, if you do think of any questions afterwards that you would like to ask Florian, then I'm sure he would be happy to answer to any questions that you can email to him. Dave, another question.
Not really a question. I just didn't want to leave silence. I hate silence. It offends me. If one was to take a really big, sort of a long distance look at this, some of your, you're talking about percentage changes in the carbon sequestered by, 40, 50%. How does that translate to the amount of carbon that is sequestered in the ocean, and should we really be paying a lot more attention to this?
Are you talking about anthropogenic CO2?
I'm talking about, the how much buffering there is in the ocean effectively. Is there a lot more than we think?
Well, there is a paper of Ricour 2024 that has been released quite recently, which talks about the effect that the sequestration needs to be looked from the export perspective and also of the release back to the atmosphere.
Mm.
And if we think that climate change could impact the export values and also the release of CO2 back to the atmosphere, it may be counterbalanced by the difference in the remineralization rate, and so the DIC, the amount of DIC that is remineralized. In terms of anthropogenic CO2, I mean, and the buffer effects, it's also mentioned in that paper. And we know that the capacity of the ocean to absorb CO2 is going to decrease.
Mm.
So I forgot the beginning of your question.
No,
or
no,
affirmation.
it's okay. Maybe you could send me a citation or send me the paper.
Yeah.
Also your
Yeah.
paper, please.
Yes.
As Adrian knows, I know absolutely nothing about biological carbon pumps, and so it's all intriguing.
So what I'll do is, I mean, Florian and Manon have kindly agreed for the talks to be recorded. So when I put those onto YouTube, I will add Florian's and Manon's papers in the subject field for that. But also we can, I'm happy to circulate around the paper by Ivy Fringer. I just tried to find it quickly on Google and failed to, otherwise I'd have put it in the chat, but I'm sure we can find that out. So I think, unless anybody's got any last questions, we're coming up to the hour. So thank you once again to our two speakers, to Manon and to Florian. Thank you for all joining the talk, and so we'll be advertising the next call in the next few weeks, hopefully. But otherwise, thank you all very much.